Hello, AP Physics. So this is strange with the long break we've had to be picking up with Gauss again, but we are picking up with Gauss again. And so just as a quick review, I tried to have myself prepped and then I forgot to write Gauss's law, so I threw it here at the bottom. Gauss's law, so we worked with flux before the break, and Gauss's law relates flux to charge enclosed by a surface. So essentially, it allows us to, if we know what charge is inside something or what charge we have, it allows us to find electric fields, because remember, flux has electric field, right? Flux is really just basically, this is the non-calculus way of writing it, but it's electric field times the surface area it pierces. Okay, so Gauss's law allows us, if we know the charge, then we can use that to find electric field, which is really useful for charge distributions that are more complex than just like 1 or 2 or 3 point charges in a triangle. So we're using this for sheets of charge, as we did before break, or wires of charge, or cubes, or now we're doing things that are more circular in nature, but where there's like a ton of different little charge particles. So if we know the charge, it allows us to find the electric field, or we could, if we know the electric field, we could find the charge. So that's kind of what Gauss's law in a nutshell allows us to do. So before the break, we practiced with finding flux. I know it's very abstract, so if you're saying, I can't even really picture this or where it's useful, that's okay right now. But the point is, we practiced with finding flux. It is a heavy calculus concept, but we are only looking at surface areas that are nice and comfortable for us. Things like rectangles and shells and cylinders. So we're not really using calculus. So we practiced with that, and the other thing we practiced with was applying Gauss's law to certain situations. So depending on the situation, you choose a Gaussian surface, which is a hypothetical surface that will enclose a charge. So we looked at how like a cylinder is a nice shape to enclose a wire. If I have a wire running like from ceiling to floor, the cylinder would enclose that in a nice symmetrical way. If you have a point charge, you can enclose that either with a cube, which you have practiced with using, or with a circle, which is what we're going to be getting into today. Or there are times when sheets of charges are helpful. So we really practiced with the cylinders, the sheets of charges, and the cube as our Gaussian surface. So what we're going to do today is get into the more circular geometry. So the first one, I'm not really going to derive these because I don't have a whole lot of space, so I'm like going to conceptually derive them. Actually, this one we already did derive. It's on YouTube already. So the two things that we see with circular geometry are uniform shells of charge and uniform spheres of charge. So what I mean by that is, I kind of drew it here. I didn't draw a Gaussian surface yet, but if I have charge in like a sort of a hollow shell, I don't know how well you can see that on the screen. So I have all these dots would be little charge things. So I have this charge making a shell, right? So, if you picture the shape, that's what it is. If you're eating Easter candy, this is like your hollow bunny, and the charge would be where the chocolate is. This is like the solid. So you have charge all throughout. So this would be spherical, as a uniform sphere of charge. Okay, so if you have either one, what we want to know is what's the electric field inside and then outside of that charge. So for this one, if you picture, let's go with inside. I mean, I tell you the answer, but if I draw a Gaussian surface, so the blue circle will be my Gaussian surface. The amount of charge enclosed by this Gaussian surface is a big fat 0. So the electric field anywhere inside the shell of charge is 0, simply because no charge is enclosed, right? So, if let's say out here to the edge of the charge is like big R, and my little blue, help if I take the cap off, my little blue circle is little r, right? If this r is less than, so it's not enclosing anything, you have an electric field of 0. Outside the shell. Now the shell theorem that I talked about a way back, the shell theorem said if you're outside the shell, so if I make outside the shell of charge, sorry. So if I make a second Gaussian surface out here, which is, let's call it R2, and it's bigger than the radius for the shell of charge. So it's enclosing all the charge now, right? In that case, we will, sorry, the shell theorem says we treat all this charge as though it's located right at the center. So the electric field would be equal to 1 over 4 pi epsilon naught, or K, times whatever charge that is. I mean, that's the total charge right there, divided by R squared, where R would be this R2. We really proved that, essentially. If I use, I'll kind of prove this one. If I use Gauss's theorem, epsilon naught times my flux is equal to Q enclosed. Flux is the electric field times the surface area. The surface area of a sphere is 4 pi r squared. Just from geometry, you know that. So that's equal to Q enclosed. And if I use this and I solve for E, this is what I end up getting. So 1 over 4 pi epsilon naught times Q over r squared. So, and again, because the AP College Board loves, and college professors, love to use the shell and spheres of charge, and they're the easiest ones, so it's great. Anytime they kind of trip you up because they're so easy. If they ask you for something inside the shell, and you'll see this as we practice problems, you just write 0. Don't even think about it. Write, well, think it's inside the shell. Write 0. That's all you do. Outside, this is it. Now, if you have a uniform sphere of charge, this would also apply. I'm not going to do a problem like this, but if I gave you a radius, I don't know if you were thinking, what if I end up with the radius like out here sort of in the middle, where I'm enclosing some of the charge but not all of it? You would do like this idea. Okay, so if I have a uniform sphere of charge and I have a Gaussian surface that is somewhere within that sphere of charge, to figure out the electric field, you end up doing a derivation. They show it to you in the book. I just don't have the space on the board. You essentially just make a ratio, like amount of charge enclosed divided by total charge enclosed is equal to this amount of volume enclosed over if this were the total volume. And you kind of do some solving. It's a cute little, it's not a nasty derivation. But you end up with this equation for the electric field. The electric field is equal to Q divided, so Q would be the charge here, of the whole sphere of charge, divided by 4 epsilon naught R cubed. This capital R would be the entire, like, again, so this would be capital R out to the, so the entire sphere, times little r, and little r would be your actual location, so this is little r. Very rarely do you actually do problems like this, but if you do, even though I just sort of wave my hands at it, you literally just plug and chug. So that's it. I think I gave you like 1 to practice with on the homework, but you don't often see it. But it comes, again, just from, this was derived from a ratio of like this volume to the full volume, this charge to the full charge. That's where it comes from. So summary arrangement gives you this equation. If you are outside the sphere of charge, this is the one they like to do more often to kind of trip you up. If you're outside of the sphere of charge, so let's say I make my Gaussian surface out here with my R bigger than big R. Well, then I'm enclosing the whole thing, right? And so that shell theorem applies again. I treat the charge that I'm enclosing as though it's all located at the center. So I just go back to my same old equation, 1 over 4 pi epsilon naught times the total charge enclosed over my R squared. So this works only when I'm outside the uniform sphere of charge. So that's all we have for circular motion. So you're either going to have shells, and the big brunt of your problems are shell problems. Just because later and more high-level electrostatics, the real world, that's where things are at more. So shells, inside 0, outside KQ over R squared, and then spheres, inside you would have to use this thing that comes from a volume ratio, outside you treat it as though you have all of it's just a point particle in the center. I did make, and I posted on, or I will post, on Schoology a cheat sheet with all the like Gauss equations for different shapes. So like cylinders, sheets of charge, shells, spheres. So you'll have that all there. And if we were seeing each other face to face, this is something I would have printed out and given to you, and just have it in front of you when you're going through these problems. What I want to do, so problems wise, they're they're pretty simple because they just give you circles and ask about different points in the circle. But there are these tricky things they can do where you are given graphs and you're asked to solve problems about graphs. In fact, I gave you one with the cylinder and I don't know how well it went or did not. So I want to go through one of those. Actually, I'm going to go through two of those. One on this video and one on a separate one that's a little bit more challenging. Okay, this is hard because I don't know how well you can see my graph on the board, so I'll kind of tell you about the values. I made this problem up, so it's a little sloppy. All right, so here's my picture that will go with it. I have a point in the middle, and then I have shell A, shell B, and pretend these are all beautiful concentric circles that they don't look like. This is shell C. These shells are thin, meaning like the radius, you know, if you hit one side of B and the other side, we say the radius is approximately the same. So they're thin, and they're non-conducting. Okay, so the graph that would come with this is this. The graph is flux out to radius. Now, the real graph had like values that you'd be reading off the y-axis. I don't think like from there, I don't know how great your eyes are, but I don't know how well if I label these you would see them. So I'll just say like, I'm going to trust if I had numbers here, you could, you know, if this was 1, 2, 3, 4, 5, you could read the graph, okay? So I'm just going to tell you what the number actually will be. I'm not even going to write them. So this is what it would look like. It would look like okay. And the values here would be -2 times 10 to the 5th. This should be, sorry, I made this wrong. Okay. +1 times 10 to the 5th. -1 times 10 to the 5th. +4 times 10 to the 5th. Okay, these are all newtons per coulomb. So what you have on this graph, flux is on your y-axis, and radius, so we're working our way out, is on your x-axis. And so the question would ask you to find the charge of the central particle, shell A, shell B, and shell C. So we want to find the charge of the central particle and shells A, B, and C. They're all charged, we just don't know what their charges are. Okay, so again, like most, I hope I'm not freaking you out here, most of the circular geometry problems are really easy. We just use those two equations I had up before and you make decisions. The graphing one is one I want to do because I thought if I say, oh, they're so easy, and then I threw this problem at you, which I did, something like this, in your homework, you might be like, what? Okay, so when you look at these, I'm trying to think of a way, I'm just going to tell you how to do it. When you look at these graphing problems, you see these obvious jumps, right? So what we're doing is we're like working our way out and suddenly we're enclosing something else and we've jumped. And working our way out radius-wise and suddenly we're enclosing something else and we jump. So that's what these things indicate. So right here, like you can see I have 1, 2, 3, 4 different flux values. Well, there are 4 possible things I can enclose, right? I can enclose the innermost particle, this has a charge. I can enclose A, I can enclose B, I can enclose C. So that's what these things correspond to. And so when and you'll always, like, they'll match up nicely every time. So when I were looking at this graph, that's what I would go, like, just label it for myself. So out to this radius, whatever it is, because I didn't write numbers, this is when I'm enclosing just the interior charge. This is when I work my way out and I'm enclosing the interior charge plus shell A. So I suddenly had to jump, right? Because I work my way out and then suddenly, boom, I'm here and I've got shell A, which has some more charge enclosed, which totally changes my flux. Here, down here is where I'm enclosing the interior charge, shell A, and shell B. And then up here is where I'm enclosing everything. Well, I can't even spell, that's a Y. Okay, so that's how you read these graphs. Again, they'll all be like that. So I'm working my way out, enclosing the first thing, now I'm enclosing the first two things, then the first three, then okay. And then you just use Gauss's law to solve. So I don't know if I'll have space on the board to go through the whole thing, but I think once I get through like the first two, you'll get the idea. Okay, so I want to figure out the charges. So Gauss's law says epsilon naught times net flux is equal to Q enclosed. Okay, well, I have net flux for each of these different places. Epsilon naught is just 8.85 times 10 to the negative 12. So I can find my charge enclosed. So first, so you work your way out. So I'm going to start with that interior charge. So I can say Q enclosed, I'm just cheating where I wrote down my numbers, is equal to epsilon naught times flux, so it's 8.85 times 10 to the negative 12, if you care about units, coulomb squared over newtons times meters squared, times my net flux, which is negative 2, and the sign is important there, times 10 to the 5th newtons per coulomb. And so if I plug that in, this gives me negative 1.77 times 10 to the negative 6, so we could say microcoulombs. And that's my charge enclosed. Okay? Now, my charge enclosed here is just the interior charge. So we would say the interior charge is equal to negative 1.77 microcoulombs. So this one, as you see, is a little bit different. I'm not actually using the equations for the spherical geometry. I'm just using Gauss's law, like straight up Gauss's law and reading a graph. Okay, what if I want to work my way out? So now I want to find the charge of shell B, or I'm sorry, shell A, for the love. Shell A is the first thing out. So shell A. Okay, so I'm going to go through to my next thing, which is right here, where I start to have shell A. So Q enclosed is equal to epsilon naught 8.85. I'm going to now leave off units because I'm being a hypocrite, but I am. Times the total flux. Well, now my total flux is 1 times 10 to the 5th newtons per coulomb. And so when I do this, I get 8.85 times 10 to the negative 7 coulombs. Now, this is my charge enclosed. My charge enclosed, which is equal to 8.85 times 10 to the negative 7, includes shell A plus the central charge. Sorry. Well, I know the central charge. That is negative 1.77 microcoulombs. So shell A, I'd have to subtract the central charge from this side. So shell A is equal to 8.85 times 10 to the negative 7 minus the central charge, which is negative 1.77 microcoulombs. And this gives me 2.655 microcoulombs. So now I know the charge of shell A. So I've got shell A, I've got the central charge. Again, I know I clearly see I'm running out of room. Let me just set up for the third one, and you, I think, get the idea of what you keep on doing. So here, let's look at this one right here. Q enclosed is equal to 8.85 times 10 to the negative 12 times my net flux, which is negative 1 times 10 to the 5th newtons per coulomb. This gives me negative 8.85 times 10 to the negative 7 coulombs. Now this charge enclosed, I'm running out of space. Can you even see me? Yeah, okay. This charge enclosed is equal to the charge of the central particle plus shell A plus shell B. I want to know what's shell B. I already know my central is negative 1.77. Shell A is positive 2.655. So I put those values in, right? So I know my total charge enclosed. I know the central charge. I know the shell A charge. I do some subtraction to find the shell B charge, right? And then again, you could go do that for the last one. So Use this value to find your total charge enclosed. This includes everything. I'll know the central A and B. Use that to find C. So it's just like you keep subtracting. Okay, so that's an example of the graphing types of problems that you can see with this. The other one should be a little bit more straightforward. Yeah, we'll see how you do with it. But I think you're going to be okay. There is one where I push it a little bit and have you look at, instead of these thin and non-conducting shells, I have you look at conducting shells. So I just want to, without doing the problem, I want to talk through a conceptual thing with that. Again, it's like a graphing thing, so it's as hard as it can get. Okay, so the question is like, what if I have something like this? So I have a central charged particle. Then I have shell A, which is not thin. This whole thing, the stuff that I'm shading in. This is shell A. Oh my. And this is, oh my, this is the ugliest circle. Oh boy. And I'm getting sloppier by the moment. Okay, this is shell B. So the point is A and B are no longer thin. And they are conducting shells. So they're made of, you know, some kind of metal, presumably, where they can conduct. Now, we talked about before break, and so that's why I want to re-emphasize this point, because I don't know how well you remember it. Conducting shells, whenever you have a conducting material, the charge always goes to the surface, right? So if you didn't remember that, just believe me. When you have a conducting material, if you have any excess charge, I should say that. If you have any excess charge, it's always going to go to the surface, kind of because conceptually they all repel each other, because they're going to be like charges, so they're going to try and push as far apart as they can. That's always on the surface. There's a lovely proof of it too. But so shell A, if it has some excess charge on it, all that charge is either going to be on this inner surface right here and or the outer surface. It'll go to both places. The point is there's not going to be charge like in the part that is very, very sloppily colored in. So it's going to be on the innermost edge and the outermost edge. The same thing is true for shell B. Innermost edge, outermost edge. So you can do graphing problems with that, but let's say that I tell you that the interior charge is positive, I'm sorry, it's negative. Let's make this negative 2 microcoulombs. And let's say that I tell you that charge A, or I'm sorry, shell A has a charge of 5 microcoulombs. And so one thing I could say, again, this is something that isn't really using the math of the circular geometry. It's more just using this conceptual Gauss's law general stuff. What if I said, how is this charge distributed? Okay, so if I have a innermost charge of negative 2 microcoulombs, again, for A, some charge can be on the inside of the shell, some charge can be on the outside of the shell. So charge is going to move on the inside of the shell, like in attraction to this negative 2, to neutralize it. So you're going to have 2 microcoulombs. So it's going to be just equal and opposite is what it always will be. So 2 microcoulombs will be distributed, positive 2, on the inside of that shell. Now, you're told that the shell has a total charge of 5 microcoulombs. So if the shell has a total charge of 5, that means that an additional 3 microcoulombs, and it's going to be positive because you need to get it to add up to 5. An additional 3 microcoulombs are going to be put on the outer shell. So the inner shell is going to try to neutralize whatever is interior to it. So that was this thing. And then the outer shell is getting me to my net charge of the shell. So if I gave it to you, then you can easily find it. Or there are ways they can make you calculate it. But and then same deal for shell B. If I say shell B has a total charge of, let's say, 0. It's a neutral shell. It's a conducting material still, so it's metal, so charge can move around easily in it, but it has a total charge of 0. How is the charge distributed in that shell? Well, if there's this interior charge of 3 on A, I'm sorry, exterior of 3 on A, the interior of B wants to neutralize that. That's just how electricity behaves. Opposite charges attract. So the interior of B is going to have a charge of -3 in response to A, right? And then the exterior of B is going to have a charge that's going to get me, oh boy, to 0. So it's going to be +3 microcoulombs. So as a full shell of conducting material, shell B has no net charge, just because I told you it didn't, but it is distributed in such a way that the interior is responding to what's happening in shell A, and again, that exterior is just going to give you your total charge is given. So that's another thing you can see with some of these circular geometry problems. That's more asking you some conceptual questions about electricity, but not using those equations that I taught at the beginning. So those are kind of the 3 things we can see with circular things. Plugging and chugging with the equations from the first bit on the board. Graphical questions, which are just really using Gauss's law, but learning how to read that graph, so how to interpret that data in the very beginning was tricky. Again, they would all look the same though, so what you just saw me do, that's how you do them all. And thirdly is dealing with, what if I have a conducting shell and kind of have to think conceptual. So again, this is like sort of the opposite charge rule. And that's it. So I will stop here. This is a long video. I hope it uploads. And say good luck with your homework, and I will see you to go over it on Wednesday.